Hello, I'm Jonathan Pallant, Senior Engineer at Ferris Systems, and we are presenting on how you can use Rust for safety-critical systems. A lot of people talk about Rust and its memory safety, so we thought we'd talk about something different, highlighting various aspects of the language that lend themselves to safety-critical systems, like the auto-generation of code. No one should ever be writing a function to print a data structure. The computer is perfectly capable of writing those functions for you. We do that with a derive macro, and the example of being able to embed test cases in your documentation. So they serve as examples when you look at the docs, but all the examples are also executed and function as test cases, which is really nice because the test cases are then right there next to the data. And because we've got the Ferrocene toolchain now, you can use that qualified toolchain for building safety critical systems. So it's ISO 262 ASIL D and IEC 61508 SIL 4.
Hello, my name is Anil Patel. I am from Rhineland-Pfalz Technical University, Kaiserslautern, Germany. I'm here to present my thesis topic about adaptive safety measures. My concept starts with traditional risk assessment methods, where in ISO 26262 we have a severity, controllability, and exposure ratings that are assigned subjectively and not using any vehicle dynamics models and so on. So what I'm trying to do here is to simulate different conditions using simulator and try to find risk-specific context information to feed my model with this information to train and collect severity and controllability ratings at runtime. Using this severity and controllability ratings, I can find where the problem is and when is the problem is. So by having those situations in the plot, I can find out which safety strategy makes more sense in which situations. So here I have three different strategies. Either we can change a component or change a parameter, or we can do both. And once we have these safety measures, we can put these safety measures on a system and the cyclic process continues. So we have different scenarios. Here in plant scenarios, we can combine with design parameters that depends on ego vehicles, the system with ADS. The non-design parameters are vehicles that are surrounding to the environment. The failure conditions like omissions, wrong value delay, and so on. And all this combined together, we have different scenarios. And all these scenarios, we can have a rich amount of information that can be fed into the data-driven models. And ultimately, we have a different severity and controllability. So this is how the process works. And once we have a lower severity and lower controllability, the process continues with different scenarios, with different combinations. And if we have a higher severity and higher controllability, we can find out where we have to do any safety measures, which part of the system needs additional safety measures, and how to make it our system safe. Thank you.
So I'm Paul Darnell from 3S Knowledge. We're a company based in Warwick in England, and we're showing our poster on SOTIF, which is safety of the intended function. And specifically in this case, it's for non-road mobile machinery. So this could be agricultural vehicles, mining trucks, machines like that. So that's our area of this, or the interest here. And SOTIF is about developing autonomous systems. So it's autonomous machinery. So it will effectively, it's level 4 autonomy, and it will drive itself, the trucks. So we're showing about the principles of SOTIF. We're showing about the process we follow to go from the identification of the hazards through to the technical solutions. We're showing about the ODD, the operational design domain, and how we try to make sure we constrain the ODD as much as possible, so it will save cost and reduce your V&V effort. Once we define the ODD, we will then analyze systematically the insufficiencies of the system. So this is how the machine learning algorithm could fail, or the sensing and perception system could fail, and we identify those insufficiencies and then specify functional improvements or other mitigations. So the key point here with a non-road mobile machinery is those insufficiencies could be mitigated from, for example, operational procedures, so special training of the operator, constraining your ODD, doing other measures that you could not do on a road vehicle. So this is the identification of the insufficiencies and making improvements. And then what we base the whole argument off here then from a safety perspective is we start with an acceptable risk threshold. So we have to be below that threshold for the product to be deemed acceptable from a risk perspective. So that's the threshold. And then by the time we start to do the verification, so this is the testing of the system with the known scenarios, we start to identify hopefully a reduction in that risk as we start to prove and evidence that the system is safe. So the risk will come down. When the risk is down to an acceptable level, we will then potentially launch the vehicle for production and for use. We will continue to monitor the operation of the system and the vehicle in market or in the environment and continually observe any potential hazards or identify any insufficiencies. So there's procedures in place to collect that data and analyse that data. If something goes wrong, which we don't expect, the risk may increase. But that's the continuous operational monitoring systems you have to have in place. So this is the principle, and then based off all of this evidence we will build a safety case. The safety case is based off standard safety case practice, and we take a very strong approach on the dialectic argument where we have to try to break the safety case and challenge the safety case in order to prove it's capable.
Okay, so what we're looking at is how do we ensure that software is safe? And what do we mean by safety? Well, the first thing is you've got to have some model of the system. You've got to understand what's there that you're trying to look at. Most of the ways that we look at software and ensure the safety is to look at it as a black box. Well, a black box really doesn't tell you anything. And the more complicated it gets, the more AI we introduce, the more knowledge we've got to have about what's going on in the black box. And there are two basic ways of modeling systems. One is the old-fashioned way, the traditional linear logical way, and that says you draw a diagram, you do the mathematical models, you basically run the computer programs, but that's all linear, it's all predetermined, that's all fixed. What you've got is you've got to understand which of these areas your system is working in. Is it a simple system? Is it a complicated system? Or is it complex, really complex, which means that it's not only difficult to understand, it actually can do things which you weren't expecting. And then you can have a chaotic system, which is, if you're in the defense system running a defense program, that's chaos. War is chaos. So these linear programs really don't get you to the place you want to be. You have to have something else. So what we're trying to do is develop models that will actually address these complex systems. And as you can see, the safety systems have been evolving, and they'll keep evolving and hopefully keep up with this lack of ignorance. And this is a system which we developed called FRAM, which can actually model these dynamic complex systems. And here, in fact, is a model of the Horizon software. And it shows quite clearly the problems that they had and why they had them. But there isn't anything like that. The post office had nothing like that. Fujitsu had nothing like that. So they've got to be a lot more intelligent in the way in which they go about it.
Okay, so essentially my focus is on large language models, the focus being the likes of ChatGPT and fine-tuning them for domain-specific uses, but also ensuring that the responses generated from them are safe for that domain-specific. So we've got two main features. One is hallucination, so ensuring the responses generated are on topic. And we do that by the promise that if we ask the same question to a human multiple times, the response is going to be semantically similar across all of their responses. So if you give a completely different semantically meaning sentence, then the idea being that that is a hallucination, it's gone off topic. And then the other one is comparing the semantic similarity to unsafe concepts within that domain. Again, taking the sentence into its latent space and comparing the similarity to the unsafe concepts in a live runtime. So it'll be a safety layer that's applied in addition to the ChatGPT safety layers and other large language models to try and promote and prevent people from training the large language models to become unsafe, which is quite an easy thing to do, I've learned very recently. So yeah, it'll be a safety layer that applies on top of them for domain-specific applications.
Yes, hello, my name is George Mason. This is my poster towards trustworthy AI, made this along with my colleague Craig Chance. We work for Fraser Nash Consultancy. What this poster is discussing three of the main thoughts that we had on trustworthy AI, which basically is, you know, ethical, assured, safe, secure AI, that kind of thing. Three areas are legislation, which is to do with like governance, you know, laws, regulations, standards, whatever. Techniques, the actual methods to ensure it. And finally, challenges, where we are, where we want to be, and what is stopping us getting there. Legislation, it's not very much at the moment. There's a few laws here and there. Regulations are starting to be developed, but they're not really there yet. Techniques, there's a lot of good techniques, but they are still in development stage as well. They can be spoofed, you know, they're not too secure, for example. Some are, some aren't. These are the challenges that are stopping trustworthy AI from existing today. As for when it will be resulting, when it's done, I couldn't say. Who knows? Decades, centuries, days, who knows? Yeah, anyway, that's it. Thank you very much.